Hi everyone, I'm going to go over to vocab really quickly in case you missed it during class. So on page 187, we are just writing some pictures and notes on our key vocab for the wave unit. There's more vocab than what's on this list, but these are just some of the key words for you to start off with. So to start with, a wave is a rhythmic disturbance caused by vibrations. Vibrations are really fast movements that carry energy across a distance. And this is our typical picture of what a wave looks like. A medium is a solid, liquid, or gas, so it's any matter that a wave can travel through. A transverse wave has this up and down motion, and water and light are types of transverse waves. In contrast, a longitudinal or compressional wave moves kind of left to right. So it has this more spring-looking motion. And this is how sound looks like and how springs also transfer energy. A standing wave, you can think about the waves in an ocean that don't really look like they're moving. They're kind of just like standing there. So these are waves that appear like they're not moving due to waves moving in opposite directions at the same time. So they kind of cancel each other out. They're not really moving like a big wave on shore, but when you're kind of deep in the ocean or in the big lake, you kind of just see these waves that kind of appear like they're standing still. And this is called a standing wave. Next is a mechanical wave. Sorry about that. So mechanical wave is any kind that passes through molecules. So this is not an electromagnetic wave, which we'll talk about later. But mechanical waves are everything else, like sound, water waves, types of light. So it needs a medium to go through. The crest is the top part of our wave. It's the maximum point of a transverse wave. Compression is in a longitudinal wave. The waves are closer together, so they carry more energy. And on 188, some more vocab. A trough is the bottom part of a wave on a transverse wave. A rarefaction is in a longitudinal wave, and that is when the waves are more spread apart, which therefore has less energy. Normal is also called resting point, and that's when there's no wave. That's what this line means. So like if I was playing music, that's what these waves represent, and then I turn it off, it would go back to a flat line. Then amplitude describes the height of the wave from normal. So that can be an upward height or a downward height. And the more amplitude, the more energy that exists in the wave. Next is wavelength, which is characterized as the distance between one crest to the next one. And this is called a wavelength. We use lambda, which is a Greek symbol, which kind of looks like this wishbone upside down Y looking letter. And that's what the shorthand is for wavelength. Next is frequency, and that's the number of wavelengths that pass. So here's an example of a high frequency. So we have lots of ups and downs going up and down, up and down. And for each time it goes up, we count that as 1 hertz. So here I have 1, 2, 3, 4, 5 hertz happening in 1 second. Versus a low frequency would be not as many ups and downs. So this one only has 1 full wave and a half. So 1.5 hertz. And hertz is the units we use to describe frequency. Finally, velocity or speed of a wavelength is described as velocity or wave speed is equal to frequency times wavelength. And the units used for that is frequencies hertz, wavelength is meters, and speed is still meters per second. And we could still use a triangle to help us solve for this. So velocity is equal to frequency times wavelength. Finally, we can read this short paragraph that helps give us some context into waves. So waves carry energy from one location to another. The crest is the highest point of a wave, and the trough is the lowest point. The distance from one crest to the next, or from one trough to the next, is called a wavelength. A wave's amplitude is the distance from the normal to the top of the crest, or the bottom of the trough. The amplitude shows how much energy the wave carries. The more energy it has, the greater the amplitude. The number of waves that pass a given point in 1 second is called frequency. The unit used to measure frequency is hertz. 1 wave per second equals 1 hertz. A wave's speed depends on the kind of wave and the material it travels through. Light waves and sound waves, for example, travel at different speeds through the air. Light waves travel faster than sound waves. That's why even though lightning and thunder are created at the same time, you see the lightning before you hear the thunder. And here's another diagram describing the parts of a transverse wave. And that was the notes on page 187 to 189.